Welcome everyone to this lecture. My name is Ling Heng Li. I'm currently a PhD candidate in the Department of Biotechnology and Delft University of Technology. In this lecture, we'll explore a specific case study to see how the fundamental knowledge you have learned can be applied. Let's start by going through what we have covered so far. In the first module, you learn a broad range of microbiological and engineering fundamental topics like environment and sustainability, microbial selection, metabolism, microbial diversity, stoichiometry and kinetics, as well as engineering aspects such as physical transport and biomass retention. These topics might seem a little bit disconnected from each other, so in this lecture, I want to bring them together using a case study to illustrate how microbiology and engineering are deeply linked. The case study we will focus on is about nitrifiers. Nitrifiers are microorganisms that contribute to nitrification, a process that converts ammonia into nitrate using oxygen as the electron acceptor. By carrying out this process, nitrifiers generate energy they need to survive and grow in their environment. So, why are nitrifiers important for the environment? Well, wastewater produced by human activity contains a lot of ammonia. If the ammonia reaches lakes or rivers without proper treatment, it can lead to eutrophication problems like algae bloom. Nitrifiers play a key role in the global nitrogen cycle, and we can harness their abilities in wastewater treatment to remove nitrogen, where nitrifiers can contribute to the process of converting ammonia to denitrogen gas, and the nitrogen gas will safely return to the atmosphere. Since nitrifiers are so important for the environment and sustainability, it's important to understand their metabolism. Metabolism can be divided into catabolism and anabolism. In catabolism, nitrifiers harvest energy through nitrification, using ammonia as the electron donor and oxygen as the electron acceptor. In anabolism, they use inorganic carbon like CO2 as their carbon source and ammonia as their nitrogen source to make new biomass. Now, to make sure of a nitrifier's ability, we first need to know how to select them from a mixed microbial community. To enrich nitrifiers, two conditions must be met. First, we must provide the substrate they need for growth. Second, we must prevent their competitors so nitrifiers have the competitive advantage. From their metabolism, we can identify what substrates are essential. Looking at the catabolism and anabolism equations, we can see that ammonia, oxygen, and CO2 are required. On the product side, notice that protons are generated. These protons lower the pH, and if they accumulate, the environment can become too acidic for nitrifiers to grow. To counter this, we must supply hydroxide ions or alkalinity to neutralize the protons. So, by analyzing the metabolic reaction, we can determine exactly what conditions and substrate are needed to support nitrifier growth. Next, let's consider competition. Because nitrifiers use oxygen, their main competitors are other microorganisms that also consume oxygen, especially at a faster rate. A very common group of such organisms is the ordinary heterotrophic organism, or OHOs. They use organic compounds and oxygen to gain energy, and they also use organics as their carbon source. OHOs tend to grow much faster than nitrifiers, which means they can easily outcompete them. However, OHOs depend on organics, while nitrifiers do not. This gives us a simple selection strategy. Don't supply organics. By removing organics from the system, we limit OHO growth and give a nitrifier a chance to dominate. Now let's see how this selection strategy translates into practice operation. In the laboratory, we can design the system to favor nitrifiers by supporting ammonia in the influent water, providing oxygen and CO2 through airflow, and using pH control. For example, adding hydroxide ions to maintain the optimal environment. These conditions supply the required substrate and prevent OHOs from growing because no organics are added. In wastewater treatment practice, things are more complex, but the selection principle remains the same. We can still use aeration and pH control, but we cannot control the composition of the incoming wastewater, which contains both ammonia and organics. To reduce competition, one effective strategy is to use an anaerobic process first. This consumes most of the organics. Then once the organic content is low, we start aeration. This timing gives nitrifier a competitive advantage and allows them to grow effectively. Finally, let's look at nitrifiers from a microbial diversity perspective. In nature, nitrification typically occurs in two steps. First, ammonia oxidation, converting ammonia to nitrite. Second, nitrite oxidation, converting nitrite to nitrate. These two steps are carried out by two groups of organisms, ammonia oxidizing bacteria, AOB, and nitrite oxidizing bacteria, NOB. From a taxonomic point of view, there are several genera within each group. Common AOB in wastewater treatment include Nitrous mona and Nitrous ococca, while typical NOB include Nitrospira, Nitrobacter, and Nitrotoga. Of course, many more exist in nature, and new ones are still being discovered. Different genera might also occupy different ecological niches. Take Nitrospira and Nitrobacter, for example. Both are NOB, but Nitrospira grows more slowly and has high affinity for nitrite, giving it an advantage in environments with low nitrite concentration. Nitrobacter, on the other hand, grows faster but has a slow affinity, so it outcompetes when nitrite levels are high. This example shows how nitrifiers illustrate the connection between metabolism, taxonomy, and ecology from the perspective of microbial diversity.